Thank you. Thank you for everyone coming out at 8 a.m. to listen to this riveting topic of conservation drainage. Hopefully I keep most of you awake through this. Last time I talked to 60 people, only 3 people fell asleep, so we'll go for better than that this time. As I introduced, I'm the watershed scientist with Shore RiverKeeper Conservancy. We're a small nonprofit located in Easton, Maryland, and we work in the Choptank, Miles, and Y watershed. And within this work, I have a lot of partners I work with from USDA, NRCS, and ARS. We've had partners with the DNR, as well as academic institutions, University of Maryland Center for Environmental Science, University of Maryland Eastern Shore, Virginia Tech, University of Illinois Extension, in addition to funding partners with National Fish and Wildlife Foundation, as well as the Chesapeake Bay Trust, as well as state partners, Maryland Department of Agriculture, as well as our local conservation districts. This has been an evolving topic for me. I started 4 years ago working at one end of conservation drainage to get to the point now where we're looking at it in a much more comprehensive way throughout the farm field. So let's give a little introduction. Why do we need drainage? So for the obvious thing, we want to get out in the fields earlier in the spring. We need trafficability. As you can see here, this tractor is completely stuck. Yeah, really. So in addition to that, by putting in tiling, we can reduce water-related plant stress. It's pretty obvious. We can lower the water table and move water away more quickly. Because of this, we can bump crop yields. When we look at corn, there's been studies that show we can increase yields by 24 to 39%. And in soybeans, we can look at about 13 to 46% increase in yield. And just to get an idea, for those, I think most people are familiar with tile drainage, but this is a basic setup. You have perforated tile lines underneath the field, approximately about 2 feet underneath the ground, and it lowers the water table so that we have good root growth. What are the different tile layouts? A lot of times we don't really realize what it looks like underneath the field because you can't see it. So in some fields we have a tile main, and then we just have parallels coming off of it, and we have some surface inlets in the field. More common practice in the Midwest is herringbone style tile, where you have a tile main right in the middle, and then you have laterals coming off either end. In addition to that, if we have a grass waterway or small stream, in some instances they'll put in double mains to intercept water before getting to that stream and move it away more quickly. And then finally you have some what we call random tile. So you might have potholes in the middle of the field that don't drain. So instead of doing this kind of layout, you'll have just these tile mains go out to the pothole, and you'll have small leads that have either surface inlets, or in this case they have one lead, and then that all goes down to one main because you don't need to drain the areas in between that have sandier soils that are well drained. Long time ago we used to put in clay, terracotta, that's why it's called tile, because it used to be terracotta pipe, and now we're starting to see what we use now is just this perforated plastic pipe, and you have these tractors that you're able to lay it. You can do miles of tile pretty quickly. And to get an idea, this is what newer surface inlets look like. They're just a tile riser, and they have openings to reduce the amount of sediment that get into it. And I'm going to go through what we're facing here in Delmarva in a minute, but what are the environmental benefits and cost of tiling? A lot of times, drainage might have a negative connotation, but there are a lot of positives. By putting in tile, you reduce the runoff from a rain event. And this is because it can saturate more water into the soil and move it slowly out of that field. So this causes a reduction in peak flows to that ditch or stream. In addition to that, we see less sediment moving because we reduce the amount of runoff from that field. With that, because phosphorus is bound to the sediment, we see a reduction in phosphorus moving off that field. In addition to that, herbicides act a lot like phosphorus. They stick to our soils, so you can see less herbicide loss off the field because we have less sediment. And there's been some instances where we see pesticide loss, but this is not as much as when we see less sediment and phosphorus moving. What are the negatives? Well, by tiling a field, we change the hydrology of that field. We're moving away groundwater that should be saturating the water table. We're putting it into a pipe and then putting it into surface waters. And because of that, we see a concentration of dissolved nutrients like nitrate, which is the major issue here because that adds to eutrophication of our local waterways. In addition to this, something that you might not think of, but if we're injecting manure, it can affect this practice because you're taking liquid manure, putting it closer to that tile line. So if you have a rain event, it's going to run off into the tile. And in addition to that, as you can see here, we're completely circumventing any kind of ecosystem services that a buffer might provide. It's going right underneath that buffer, discharging right to waters. So on the eastern shore, what are we looking at? So this is a field. This is actually just south of Greensboro, Maryland, which is just north of Denton. So on the Delmarva, we see a lot of random tile. And you can see here we have a bunch of potholes in this field that are not draining well, and each of these has a tile well inlet. Some of the fields we see cinder blocks that are made into a square, and you can't really see in the picture here, but there's 3 tile lines that come into this basin here. And these basins help move surface water out of those potholes. Some newer ones are these circular concrete structures, and you see the tile going out right there. So these were put in from the 80s, and some of them are continually being put in, but we have newer structures now, like that tile riser that I showed earlier, that actually just has slits in a pipe. A lot of our tile line is clay. A lot of it was laid from the 1950s on, and you'll see these, and they're still operating to some degree because they're so strong. I didn't bring a piece of it here, but a lot of tile, if you have a 10-inch tile, it's really 12-inch in diameter, and it's an inch thick of clay tile, and it's 2.5-foot sections. So a lot of this stuff is heavy. It is still operating to some degree. Some people don't realize how much tiling we have on the eastern shore. I know one contractor's put in over 380 miles of tile, and that's just since the 1980s. So there's a lot of other tile out there pre-1980s that's been laid, and there's other contractors out there that put it in. So it's, over 2 million linear feet. What we're seeing now is some conversion of ditches to tile, and that's because we're running more irrigation. It's a lot easier to run irrigation over a closed ditch, so you just tile it. It also gets around some regulations about spreading. And a lot of it, as I said, is pre-1980. So that raises some issues. So when we look at water coming out of the tiles on Delmarva, these are 3 different sites, mostly located in the Chop Tank watershed. And this is going from August until April. So it's over a year of data collection. And then you can see here, this is nitrate in milligrams per liter. So the drinking water standard is 10 milligrams per liter. And what we're seeing here is what's happening is that the tile lines are intercepting this water before there's any kind of treatment from the ecosystem. Generally, what we see is about an average of 10 milligrams per liter coming out of our tile lines, but you can see there's some spikes here, upwards of 50 in some instances, but around 30. And those can happen during late season storm events where the field is drying out, nitrate has been sitting there, the corn crop is drying out, and you have all this heat that's metabolizing all of this organic nitrogen into nitrate. It rains, it gets washed into the tile lines. This is like here in August where we have really high concentrations leaving and going into our ditches. So that's the issue there, is it adds to that algal bloom that's happening there, and potential other downstream impacts. But in addition to this, a lot of our infrastructure is old, and it's really costly to repair. So this is what those old tile well inlets look like, and you can see it goes right to the surface here, and this is one that we're replacing. In other instances, that clay tile is failing, and you're getting suck holes in fields. That's fairly common, and you replace those as they go. It's not a whole tile line replacement because that can cost over $10,000 to $20,000 to do that, so you're just going to replace that section that fails, and then another section fails further down on the line. And this is the site that recently, you can see here, they powered it to get water to that surface inlet, and you can see the erosion that's happening in that field, and it's not even draining properly. It's flooding out the crop there, he's losing yields, and he's losing all that topsoil. And this pipe is the outlet. You can see it's still functioning, there's water here, but over the decades that it's been moving in so much sediment, it's clogging it up. And this is that ditch that it's going to. In other instances, we see these newer boxes, the cement ones, and it's eroding down and cracked the pipe at where intersection there. So you can see this rill erosion coming in. It's coming in, turning into gully erosion, moving sediment, and then the field itself, you can see a pothole, or not a pothole, a suck hole in the field right here. And this is what the pipe looks like coming out of that. This was put in the early 1980s, still functioning even with all these issues. So what is conservation drainage? I pulled this quote from the Minnesota Department of Agriculture. This idea of conservation drainage really started in the Midwest, where tiling is everywhere. They define it as several emerging technologies and methods that provide the benefits of conventional agricultural drainage. So we still want to maintain good drainage, get these fields to pull down the water, but we also want to reduce nitrates and other pollutants that are going into our waterways. So it's kind of looking for a win-win opportunity here, is where we maintain good drainage, but also are able to treat the nitrogen, phosphorus, and sediment coming out of our fields. So for the example of what we're doing here on the Eastern Shore, I'm pulling this from a project I'm working with USDA in Delaware, NRCS. I got to call out Rich in the back of the room. This is his design. I'm going to pull him up here and make him talk about it maybe. This is happening, it's in the Marshy Hope watershed, which is part of the Nanacoke. And this is the tile line setup here. The original line is this dotted red right here. Our new setup is this purple line here. And to get a better idea of what it looks like infield, you can see we have 3 inlets up here in this lower area that doesn't drain. These are really heavy soils up here, and then it goes through a small sand ridge, and this tile line keeps going down, and then eventually outlets into a small low area here that goes into a ditch right to the Marshy Hope. So the first part I want to focus on is up in this area here, discussing of what we're doing with these surface inlets to make them a more effective practice. Zooming in here, as I said, here's the well, the existing wells, then the existing tile line itself. This is a 6-inch tile out there, and then the proposed retrofit here of what we call a blind inlet. And you can see these square boxes here are the blind inlets. So this is the current conditions out there. It just basically looks like a sewer drain right at the field surface. Fairly common, I'm sure a lot of you have seen that before in fields. And each of these look like this. And as you can see, the effectiveness, it's not draining down the water, there's stuff growing around them, there's sediment getting into them. And then this is from just sampling here about 2 weeks ago. Pretty minor storm event. We had an inch of rain over about 10 hours, so it barely caused a runoff event to occur, but even though the only 2 hours that it ran off, you can see what came out of that tile line. And this is just all that debris that was sitting on the field just got washed in. So what is a blind inlet? So we're going from this surface inlet here to what looks more like a French drain structure. We have PVC pipe in here that's perforated. Then we have number 4 limestone that we put in. Around this, we have geotextile fabric to keep the soil from migrating in. And then we have coarse sand laid over top of that, mixed in with a little bit of soil. And just to get the basic dimensions, this is the plan view here. You can see that the perforated PVC, we have a solid line coming out that goes to the tile main. It tees off at that tile main. And then just looking at cross-section view, we have about 18 inches of soil on top of this, about at least 20 inches of limestone put in there. And then the pipe doesn't sit directly on the bottom. It's actually sitting on a little bit of limestone on top of that to make sure that we can move as much water as possible through this system. And NRCS currently has a nice calculator that we can use to figure out the sizing of this. What we want to drain down is about a 2-year, 24-hour storm event, which on the Delmarva is between 3.5 to 4 inches of rain. And then we want to do it within 24 hours. So once you put in all of your different field calculations here, you can figure out what kind of length and width you need. And in this instance, we're looking at 22 feet long by 15 feet wide. If anyone has questions during any of this, please call them out. I don't want to skip over anything, or if anything's unclear.
What kind of pipe is that?
The Schedule 40 PVC inside? It's just, yep. Yeah, you'll probably have to drill them in, or you might be able to use septic drain field kind of pipes. And the holes are at 4 and 8 o'clock so that it's not directly in the bottom of the pipe. So what are we looking at for blind inlet considerations here? It has a 10-year lifespan. That's pretty standard for any NRCS practice. They've been in the field longer than that. They encourage 100% no-till, which makes sense. We want to have water moving through those soils. We don't want a pan layer over top causing the water not to be able to make it into that blind inlet. Once it's installed, there's almost no maintenance. You could, if the field starts getting clogged up, you could do gypsum application to increase porosity and move the water through the soils. The great thing is they do not impede farm machinery like the old surface inlets. You can drive right across this, you can plant right into it, you can do light tilling right across it, you don't have to worry about it. And obviously you need to have functioning downstream drainage or else it's going to clog and back water up into the field. To get an idea, this is what a blind inlet in the Midwest looks like after 3 years. You can see he planted the soybeans right into it. Obviously it's not going to grow as well in that small section because you're draining out the water there, but you're still able to go straight through it. What are we looking at for reductions? So compared to just a typical tile riser, we're seeing reductions in sediment load by 79%. So that's something that you can show to the farmer that you're not losing your topsoil, and you're also not losing your phosphorus, one of the key nutrients there.
Particulate phosphorus?
Yes. So there is, if you can see at the end here, some soluble reactive phosphorus has been removed in some instances. And if you're at the presentation, I think yesterday, Chad Penn discussed phosphorus removal structures. He's been working on these things, and instead of limestone, you can use the slag material in it. But then you're going to have maintenance issues because after a while, that slag is going to be totally absorbed with phosphorus, and it's not going to be as effective. So after a few years, you have to replace the slag within that blind inlet. But if there is a large issue with soluble reactive phosphorus, in the lower shore we have a lot of high phosphorus fields, you can put slag into these to remove that. I think you can see they've been out in the field for 12 years, and even though sediment comes over it, the flow rates didn't decrease. So there's the 10-year standard, but they've been out there for 12 years still functioning perfectly. So what we're looking for outlet practices. So we got the infield cover, we're reducing sediment and phosphorus infield, but obviously nitrogen is a little bit different. It's soluble, it moves with the water, and it's not going to be able to be treated in these blind inlets because the blind inlet's purpose is to move water out of the field. So a newer practice is what we call a saturated buffer. So in this instance, you have the outlet pipe coming out, but instead of that, you have put in this case, they're using an agrodrain box, a custom-built agrodrain box, diverting water into the buffer here in a perforated pipe, and using this buffer to get rid of those nutrients, to use denitrification in the soils, as well as uptake by the plants. And this is the basic setup here. You have the tile main coming out of the field, you put in your box, and this is a 3-chambered box in some instances. We prefer 3 chambers mainly because then you have the ability to adjust the water level in the field as well as adjust the water level going into the saturated buffer here. So this middle chamber is going to be diverting that water to the buffer, and then there's the perforated pipe that goes into it, and you can see it just runs along the buffer. And the basic idea is just to use this as a natural process, enhance what the buffer's doing already for that system, and take up the excess nitrogen in the groundwater that's moving through that tile. NRCS does have an Excel spreadsheet to do the calculations here. What we want to achieve is at least treating 5% of the minimum or the maximum discharge coming out of that tile line. And there's different ways you can do it. You can do it through just the tile line configuration or the drainage coefficient, or if you model the system, you can use drain mod as another way to do all of that. So in this instance, we came up with a length of 400 feet in order to get to that 5%. And you can see all the calculations that go through here. And then if you have any questions, I'd be happy to discuss this later. Another great resource is Rich, who went through this process with me, if you have any questions on these calculations. They're really tiny on here, so it's kind of hard to describe them.
What depth is that?
The pipe?
That pipe?
It's going to be about, they want it to be setting within at least, the water set up about at least within 2 feet of the root zone, if I remember correctly. So that pipe is not going to be any deeper than 2 feet in to the ground generally. But the water level is going to be kind of set by the box itself, because as you can imagine, if this is 2 feet down and then the water's level set at 1 foot there, it's going to be flooding the root zone to a foot. So that's kind of where you have the ability to adjust it, with that flashboard there to adjust the water height. So what are we looking for? What kind of buffer width do we need? Minimally, we want a 30-foot buffer. Bigger than that is great. And as you can see here, the nitrogen removal effectiveness of a buffer obviously goes up with the size. So anything below 30 feet, it's hit or miss whether or not you're going to get any kind of removal. Once you get above 30 feet, you can see 50 feet here, much more effective. And once you get even further out, over 100 feet, you're removing most of the nitrogen that's moving through the groundwater. And then for soils, we want organic soils, obviously. We need the organic material for denitrification to occur because you need a carbon source. What we don't want to find are soils, organic soils, underlain by sand and gravel, which we have a lot of here on the eastern shore of Maryland, as probably many of you know. So if that happens, then you're going to have preferential flow routes, and the water's just going to move into that sand and gravel and then move away really quick into the stream, and there'll be no treatment. And if we get a restrictive layer, that's even better, because then we know the groundwater's going to be hitting that and staying within that organic soil and not moving further down into the groundwater. Some other considerations. Because we're saturating the buffer, we have to think about what's happening in the channel and the receiving waters. So under perfect conditions, we're going to saturate it up to that root zone, a foot from the surface, and then it's going to drain down to the water level in that stream or ditch. In other instances, we might have a deeply incised channel, and the issue we have here is the water's going to seep out higher. And obviously, freeze thaw and everything else, we're going to cause that bank to fail, and we don't want to see that happen. We're trying to address a resource concern, not create another resource concern. In addition to that, one of the biggest things we face here on the eastern shore is this flat topography. I don't want to backwater up in the buffer and then flood out the field underneath and kill a crop. So these are all the kind of things we need to think about when we think about placement within a topography. So what's the effectiveness? How well are these things working? This is a setup in the Midwest. The box is put here. You can see the lines coming off, and they have wells here to monitor the groundwater. So how much water were they able to divert into the saturated buffer? Because that's what we're trying to aim. We're trying to get as much water out of that tile and into the buffer. It's really variable between years. As you can see, some years they're diverting over half of the water in the tile into that buffer. So that means you're getting good treatment. Other years, you're only diverting 35% in this year and 25% in this year. And a lot of that has to do with what kind of storms you have. Higher intensity storms, you're going to have more bypass flow because you're going to have the higher maximum flows in the tile. If you have a year where it's just, soaking rains, then you're going to be able to treat more because it's not moving as fast. And in the field itself, I know it's terrible to use tables like this because it's really overwhelming to look at, but it's pretty straightforward. So you have the transect of wells that were down from the saturated buffer. So one was pretty close to the tile line for that buffer, and then they go further away. And the takeaway message here is you start with fairly high nitrate concentrations between about 7 and 10 milligrams per liter, and by the time you get halfway through that buffer, it's almost all removed. And once you get to the end here, it's all gone, less than 0.3, so they couldn't detect it within that buffer water. So nearly 100% nitrate removal is occurring in a lot of these saturated buffer applications in the Midwest. So what are the costs? So that custom box, I've had to order a lot of them. So generally they're about $1,000 to $2,000. If they're really big, you can get $3,000 to $4,000. Survey design contractor, general costs here are between $2,000 to $1,000 if you're using a private firm. And then we're looking at about $7 to $12 per linear foot of pipe laid, depending on the pipe size. About a 10-inch pipe costs $11 to $12 per linear foot for a tile line on the eastern shore. So total costs are within $5,000 to $6,000. And this equates, though, to only about 55 cents per pound of nitrogen. So highly effective practice for the cost. And in this instance, we're assuming it's going to be effective for a 20-year period, and within that study, they say there are about 550 pounds of N removed per year. So that's how we can get such a low cost. There is equip available for this practice in the state of Maryland for this next year. I can't remember the exact cost for it at this point, but those should be coming available. Either they came available already or should be available soon. So now on to denitrifying bioreactors. And this is where I got my start with Midshore. Is we installed the first bioreactor in the state of Maryland. This was back in 2013. This isn't in itself. This is the third bioreactor we put in, and this is just outside of Denton, near Burrsville. And the idea here is you can see there's the ditch. There's a 10-inch clay terracotta pipe coming into this ditch. It flows most of the year. It dries up around August. And it was averaging about 14 milligrams per liter of nitrogen coming out of that tile. So we're going from this setup to diverting water into a wood chip trench. And to get an idea of that setup, this is more or less what we had in that field. Tile lines in the field. We have the same kind of diversion box as that saturated buffer. You know, it's 3 chambers. The middle chamber is diverting water into the practice itself. The first stop logs can be used to back water in the tile if you want to try to keep water table higher in the summer. The other one is to set the water table height inside the practice itself. And the great thing is, just like a saturated buffer, any high flows can bypass. We can make sure we're not flooding out the field. So this then gets diverted into a trench of wood chips, and within there, it's using the bacteria, which are natural. You don't need to inoculate it. They're going to be there regardless. And the high nitrogen, and eventually it uses up, the bacteria uses up all the oxygen, so then it goes into scavenging nitrogen in order to complete its life processes. So by the end of it, it's converting nitrate into dinitrogen gas, which makes up about 77% of our atmosphere. At the end of it, you have another box here, and it has one set of flashboards, and that's to maintain water levels within the practice itself. Because we have so many ditch miles on the eastern shore, we've been trying to apply these to ditches. Similar setup, we just have a larger box in the ditch. And we've used up to about a 24-inch pipe in ditch with a box that's 5 to 6 feet tall within that ditch. It's just like your structure for water control that we've been doing for a while here. Same idea, divert water into a wood chip trench, use that natural process to get rid of the nitrogen, and then put it back into that stream or ditch. Just to get an idea of setup here, this is that location, that wood chip trench. This is what that box looks like. This was about a 5-inch or 5-foot box, if I remember correctly, coming from a 10-inch line. And we actually used a 12-inch line going into the bioreactor to get as much water pushed into the bioreactor as possible. And this is just kind of looking down to where the outlet is down here. So we're excavating it. And then we used a 20 or 24 millimeter pond liner to line it. We need to make sure it's lined so the water doesn't escape out of the practice. And then we're using a perforated pipe here to get water. So it comes to a T, and then we have this, it's kind of like a level lip spreader, so we make sure that we saturate the whole practice. And then we're using wood chips. We've used donated wood chips from Queen Anne's County Park before, and that didn't really turn out well because it's too mixed, there's too many organics. So we actually just started using a local forestry supplier because you want a really 1-inch kind of chip to make sure that you have good water flow through the system. So it might cost a little bit more than getting something donated, but in the end you get a better product and the practice is going to work better. In this instance, this trench was about 2 to 3 feet deep throughout. And we cover this back with geotextile, and then you cover it back with the dirt. And by the end of it, you don't even know it's there. So you bring people out to these practices as demonstrations, and there's not much to see. You see a box, and you don't see anything else. So it's a lot better to see it from the pictures during construction. And the great thing is, we've worked with this to keep them in CREP or CRP buffers. You'll just have to work with FSA to sign off that you're going to reseed it to the appropriate mixture so that the landowner doesn't lose out on their payments. So it can work within those systems, just work with FSA to make sure you discuss that. Just like with the other practices, NRCS is kind enough to give us calculators for this. We're looking to try to treat about 20% of the peak flow. And within the bioreactor itself, we want to keep the water in there for about 6 to 8 hours. If it's too short, it's not going to cause denitrification to occur because we can't get all the oxygen out. If it's too long, then it's going to have complete nitrogen removal, and then we're going to move into other reductions, so sulfate, and then we get into like methylation of mercury, which is not good because that's very toxic to aquatic organisms. So by using this, we can figure out the appropriate length to get that 20% of that peak flow in it. In a lot of instances, we're looking at sizes of about 30 feet wide by 100 to 115 feet long. So it's not a huge practice. It doesn't take land out of production. So that's been the selling point, is that we can fit it within these buffer areas. So what is the effectiveness? This is even worse than the table before, but it's really showing basic information here. So the black dot here is nitrogen coming in, and then this circle here is nitrogen leaving the bioreactor. So in these two sites, we've had 100% concentration reduction. The difference is, though, at one site, we were only able to get a 9% or 16%, depending on the year that we studied it, load reduction. And that's because we didn't size it appropriately. We would like to see between about 30 and 60% load reduction if we size it to the right size, but in this instance, there's too much water in that tile. We couldn't treat it the appropriate amount, so we only saw 9% to 16% load reduction. At the other site where we did a better job sizing, we saw a 62% and 47% nitrate load reduction, which is what we kind of target, and what we find is happening in the Midwest is what we can usually get for a nitrate load reduction. So what are the considerations? This practice is very costly, $20,000 to $30,000, and in the Midwest, it's been costing about 8 to 15, and that's just contractor costs. Here in the Mid-Atlantic are a lot different. We need to think about the drainage area. We can't have a huge site if we're doing this in a ditch. We don't want like 200 acres coming in. We want somewhere between about 20 and 80 acres draining to this site. Generally because the more drainage, the larger the bioreactor needs to be in order to treat that amount of water. And then finally, like I said before, we need to consider flow through the bioreactor. We want to make sure that we're getting the retention time we need and it's not flowing too quickly. There is EQIP funding available for bioreactors, and last year it was $43.60 per cubic yard of material. So that it should equate to about 50 to 75% of cost. And finally, we're talking about drainage water management. So this is just using that structure for water control to optimize crop yield, but also have it back up water into the soils for nitrogen uptake and denitrification. Because obviously we don't need to drain a field all year long. The middle of winter, we don't need to be moving water quickly out of that field. And the basic idea here, on the eastern shore of Maryland, a lot of times we use these in ditches. And in this instance, this graphic is showing what's happening as we back water up. It's going to that root zone, the nitrogen's being taken out, and denitrification is also reducing it into nitrogen gas. But in addition to that, we're pushing water out into the field more, so there's some there for the crops. Same idea in the tile line, but instead of having that buffer there, we're using the organic material in the crop field itself to get the same processes to occur. So this is what a drainage water management plan looks like. You can use a technical service provider to make this plan for a farmer. And the idea is that in the winter, we're going to have those boards set high, 12 to 18 inches from the top of the soil. And then as soon as March comes around, we're going to drop them to about 3 feet below the surface. And that's so we can drain the water out of that field. They can get out, plant it, and as soon as we plant it, we're going to put those boards right back up, so 18 to 24 inches from the bottom of the surface. And the idea here is then we start following that root growth. We're going to move those boards throughout the year so that the water's at an appropriate level so that we can get good crop growth, and using that water control structure to our advantage. And as we come back around, put the boards back in the winter so we're not just draining out the field during the winter period when nothing's happening. So what are these hurdles to implementation? Oh, this is drainage water management is, what is it, CSP 130 is the what you can go through for that. The big hurdle that we face is you cannot cost share tile. You might find a site, you have perfect infield conditions that you need to replace a failing surface inlet. you have high nitrogen coming out of your tile line, but if it's deemed failing, you can't go through a cost share for that. So that's where we get here, that if you see like this happening, you go in the field and you just can't replace that. So you have that resource concern that you cannot address with the cost share funding that we have available. And in a lot of instances, if you talk to a farmer, they're not going to replace it if it's still draining their field. It's just too costly. You know, $11 per linear foot of tile, and they might have, you know, 3,000 linear feet. That's way too expensive for a farmer to replace, and they're just going to do it piecemeal, and you're going to have that issue the whole time. So currently, we just got funded through the National Fish and Wildlife Foundation to do a demonstration conservation drainage program on the eastern shore of Maryland. The idea is to create a program structure to remove the hurdles for the landowner or farmer in order to put these practices in. So right now, the basic setup, what we're thinking about is we're going to be cost sharing tile at about 70%. So the farmer or landowner is going to have to pay 30% of the cost. But with that, they have to do the infield blind inlet practice, and they have to do one of the outlet practices. So structure for water control, saturated buffer, or bioreactor. And we're going to be cost sharing the infield and outlet practices at 95%. So it's a little bit more incentive than what we see through EQIP or Maryland Agricultural Cost Share that does it at 75 or about 87.5%. And this is for the total project budget right now. We're kind of estimating the cost to the farmer or landowner between $4,750 to about $6,000, depending on size of the project and the outlet practice, with total project costs between $26,000 and about $50,000 per project. We're looking to try to do about 8 projects between the Pocomoke, Nanticoke, Choptank, and Chester River. And we'll be monitoring them all because we need to get enough data to show that these practices work, and we need to start amending some standards in order to get cost share for that tile line. And this goes into the transferability, the long-term sustainability at a state or federal level. So the first option that we thought was just a standalone program. Go to the state, ask for a budget line item that says this is just for conservation drainage. You sign up, you can do these practices within it. And then you're just going to rank them based on criteria. You know, do they have the old cinder block well inlets coming in? Do they have a bunch of sinkholes in their tile? And then you can just use flat rates, which makes it really easy to do the program. But within that, we're not looking to replace completely failed tile. I don't want to go out in the field and see a tile that's not draining at all. I'm not going to replace that because it's not a resource concern at that point. It's an agronomic concern, but not a resource concern. A second option, after talking to some of the partners on this, is to use federal EQIP and MAX funding and then try to, 5 minutes out. Federal EQIP and MAX funding in order to pay for that tile line. So this goes through, you need to amend the practice standard, which means we need to collect a lot of high quality data to show that by doing a whole comprehensive retrofit, we're getting larger sediment and nitrogen load reductions than just doing the standalone parts of this project. What you might run into though is a lot of variable rates there, and you can't really set what you're going to pay for a project. And then the final option, when another partner on this grant is thinking about, is somehow using the Maryland state-run nutrient trading program to create an additional budget line item through that. So if you have someone that needs to offset their loading into a creek, say on the western shore, they can do a nutrient trade with a farmer on the eastern shore and help pay for the installation of these kind of practices. So this is what we're working on to try to get this kick-started on the eastern shore of Maryland. So with that, I will take any questions that you might have. Thank you.